Hey guys, sorry about the delay in posting these videos. I've been kind of bogged down with a crazy amount of classes and videos that required doing and grading and things like that. So today we are going to look at section 3.1, which is the first section in Unit 4. And this is kind of like an introductory section into relations and functions, and we're going to do a lot with functions this semester. I mean, this unit, but this is kind of just the beginning. So, a relation is just a correspondence between two numbers, and a function is a very specific type of relation. So, in the past, we've graphed using tables. The linear equation that we graphed, or maybe you graphed a quadratic with a table, creates a correspondence. And you can look at the x and y values in the correspondence to determine whether or not it is a function. So, for example, if you have x's and y's joined together as ordered pairs, those ordered pairs become the relation. Each x in the set of ordered pairs that we have is called the domain. By definition, the domain is any x value that you could put into a function that makes the function defined. And there are lots and lots and lots of values that can make a function defined. So we're going to talk more about that later. But um, we're going to get into kind of like the basics first. So domain is the set of all the x's. The range is the set of all the y values from the table or the set of ordered pairs. And again, when they match up together in the ordered pair, it's the relation. And then you can look at it to determine if it's a function. In order for a relation to be a function, each member of the domain is only allowed to go with one member of the range. So you cannot have repeated domain values, otherwise it is not a function. However, you can have repeated range values. So we're going to look at a couple different things. The first one is given a mapping or some ordered pairs. And the ordered pairs could be in um, set notation, or they could be in table form. They could be on a graph, but you have a finite number of ordered pairs. So we're going to look at the individual numbers here. So I'm going to do two examples. The first example is an example of a mapping. And a mapping is typically set up with x's and y's in ovals next to each other, like this. And there are some numbers in there: -3, 5, 0, 1, 2, 9. The x list here is the set of the domain, and the y list is the set for the range. The correspondence is indicated with arrows going from one domain value over to a range value. That's down too far. And that's how you tell what the relation is. These arrows are terrible. It'd be better off I'm just going to draw them myself. Ugh. Leave that one. So the correspondence is demonstrated between a domain value and a range value with an arrow. In a mapping, as long as each domain value only has one arrow coming from it, it is a function. But as soon as you have an arrow coming out twice, it means it's mapping to two different locations, which would make it not a function. This mapping is an example of a function. Now, in a set of ordered pairs, you'll have it in set notation, 5, 7, 4, 1, 5, -3, 6, 1. The ordered pairs in this set are the correspondents themselves. And what you're looking for in a set of ordered pairs or in a table is, do we have any repeated domain values? If you see any domain values in there more than once, then it is not a function. For example, 5 and 5. 5 is mapping with 7, and it's also mapping with -3, which is not allowed when you are dealing with functions. So this is not a function. So no repeated domains. Those types of relations we just looked at are called finite relations because you can see every single piece that belongs to the relation. When you're dealing with pictures of graphs, a lot of times you are dealing with infinite relations, which means that there's no way to actually tell what every single ordered pair would be on the relation. So we're just going to look at two kind of generic pieces here for now. And the first one I want to look at looks like this. It's a parabola. The second one looks like this, which we have not seen before, but it's okay. And it doesn't matter if it looks exactly like this, as long as the general shape is similar. And so here we're looking at infinite sets of numbers, because not only are there integers on this thing, there are fractions and decimals on there as well. So there's no way to really name them all, because you'd be doing it forever and still not be done. All right, what we do in this situation is take a look at something called the vertical line test. The vertical line test says that you should be able to put a vertical line anywhere on this graph, and when you put it on there, it would only touch the graph one time. If there is any scenario whatsoever where you put a vertical line on the graph and it touches it more than one time, it is not a function. That would be a failure of the vertical line test. So we have two examples here, one of each. The first one is a parabola, which is the graph of a quadratic. And I could put a vertical line anywhere on this graph. And every single one of these vertical lines that I would draw would only touch the graph one time. So as long as it never touches more than once along the way, it passes the vertical line test, and it is a function. Now, if you take a look at this second example, I can throw a vertical line on almost everywhere on this graph, and it's going to touch more than once. Once at the top on this top line and once at the bottom underneath. This means this is a failure of the vertical line test. And if it fails the vertical line test, then it cannot be a function. So it's a visual test. And you're welcome to draw vertical lines all over it like I did in the first example, but you don't have to. All you need is to imagine that one is there and it's a problem or not a problem. So that's how you determine whether or not something is a function given a picture. Now on to function notation. Now in the past we have worked with equations, and when we were working with equations or expressions, we typically wrote them as y equals some stuff. And if we wanted to evaluate the function, or equation rather, at some value, we said evaluate it when x equals whatever. In this case, it's -2. Now we're going to be writing the same types of equations in function notation. Function notation looks like this. And this is the most generic form of it. It doesn't have to be f of x. But function notation gives the name of a function, that's the letter in the front, and the variable in the function, which is the letter in parentheses. If we are wanting to evaluate a function, that x will be replaced with a value. If we are wanting to simplify the function, that x will be replaced with an expression. It is read aloud f of x. It means function f using variable x. Now, there are two different scenarios we are going to see when dealing with these functions. The first one is evaluating it at a given value. So when you see f of -3, that means you are going to be replacing the x in the function with the -3 and then evaluating. So f of -3 would be -3 times -3 squared minus 2 times -3 plus 7. Anywhere I saw an x, I put in a -3. Now, once the value has been inputted, you want to go through and use the order of operations to simplify. For example, exponents first, then back through and all the multiplication. -3 times 9 is -27. -2 times -3 is 6. And then lastly, all this addition, just combining all of those values together. -27 plus 6 plus 7 is -14. Now, these two values have names. This is called the input, and it is the x value. This -14 we just found is called the output, and it is the y value. Remember, x's and y's make up the domain and range. So the x would be involved in the domain, y would be involved in the range. Now, we might not be evaluating at an actual number. Instead, we might be evaluating at an expression. This entire expression becomes the input, which means that we are going to put it in the place of the x. And when we do that, typically we use parentheses so that we don't mess this thing up. So 3x minus 2 being squared plus 2 times 3x minus 2 minus 4. Now, in this scenario, we're still going to follow the order of operations, but it's unlikely that we are going to end up with a value because we'd have to get a lot of stuff to solve. So I'm going to start with my exponents, and I'm squaring a binomial. So when I square a binomial, I have to actually FOIL it out with itself. And I'm going to take and FOIL this thing. 3x times 3x is 9x squared. 3x times -2 is -6x. -2 times 3 is -6x. -2 times -2 is 4. So there's my exponent. I can also go ahead and just do this distribution real quick. 2 times 3 is 6x. 2 times -2 is -4. And then the -4 at the end, it doesn't just disappear. Do the exponent and the distribution kind of in the same line there. Then that way I just save some time and some writing. Because I'm going to have to go back through and collect the like terms anyway. So I'm going to start with my 9x squared, which doesn't have a like term. And then I have some like term stuff here because I've got -6x minus another 6x plus 6x. And that gives me -6 minus 6 plus 6. That's -6. That's so many sixes. -6x. And then I've got all these 4s to collect as well. +4, -4, -4. Plus 4 minus 4 minus 4 gives me minus 4. And now that's all you're going to do with this. You're going to combine the like terms. If stuff cancels, great. If not, oh well. We combine like terms, and whatever we get, we get. I already mentioned this little note down here at the bottom, how the input is the X and the output is the Y. So you could put the input and output together as an ordered pair if you needed to or wanted to. All right, part C, finding domain and range. Couple different scenarios here as well. First one is the easiest because, again, it's dealing with finite sets, given a set of ordered pairs. The domain is going to be all the X values written in set notation. Range is the Y values in set notation. And we are not going to list out any repeated values. Once something is in a set, you don't have to put it back in there again. It is weird. Somebody just walked in and said it's weird when I'm doing this. It is. I'm just sitting here talking to my computer, to other people. They don't think about it as me talking to you. And I guess I never thought about what it would look like to see somebody sitting there talking to their computer. But anyway, it's necessary, right? So, set notation, no repeats. Find the domain and range. Domain. Set notation, listing the X's. They can be listed in any order that you want. Typically, I list them in the order I see them in, even if it's not numeric order. It doesn't matter. Set notation does not have to be organized in numeric order. So the X's in this set are 3, 5, and 7. Now, if you look at the range, the Y values for all of these ordered pairs are the same, and we are not going to list repeated values. So once I put 1 in there from the first ordered pair, I don't have to put the rest of the ones in. So I'm just going to close it off. And there's your domain and range. Finite, nice and neat, in order. Second thing here is given a picture. Now, this is a little bit different because we have to kind of analyze what's going on. I'm glad that the pictures showed up in color because that is helpful. I want to go ahead and put some arrows on the ends of this. And we need to remember that domain deals with X's only. And we're also looking at the horizontal axis. So we're dealing with left-hand side of the graph to the right-hand side of the graph. On the horizontal axis, the left side of the graph is negative infinity and the right side is positive infinity. So when I'm dealing in domain, I go from the left to the right. If there are arrows on either side of my graph, on the left-hand side or the right-hand side, those arrows would correspond with that appropriate infinity. It doesn't matter if they're pointing up or down because up and down has to do with range. And right now we're only dealing with domain, which is left and right. So when I look at this picture for part A, on the left-hand side of my graph, I have an arrow, which means that I'm going towards left infinity, which is a negative infinity. Then I follow my graph along and it kind of does some little dippy things and stuff and goes over here to the right-hand side. On the right-hand side, I have an arrow as well, which means I'm going to the right infinity, which is positive infinity. So my domain for this graph is round parenthesis, negative infinity, comma, infinity. Now, once you are done with your domain, you switch gears entirely. It doesn't matter what happened with the domain. We're ignoring that now. Now I want to look at what's happening with the y from bottom to top. Bottom to top. That means the lowest place on the graph and the highest place on the graph. This is where you would look to see if you had a down arrow or an up arrow. Now on our graph, the lowest thing on this graph is not an arrow at all, but instead this point right here. That's the lowest place this graph goes. And since we're dealing with the range now, we want the y coordinate of this point. And the y coordinate is -3. Now it is a closed solid point. And in interval notation, a closed point would be represented with a square bracket. So that's the lowest part. Now the highest part is up here at the top, and it's either one of these two things because they're both the highest part. Up arrows. Arrows pointing up on the y are going towards positive infinity. So my highest point is infinity, round. Infinities always take a round, just as a reminder. That is a picture of a quartic function. Hang on one second. My husband is texting me about FMLA leave, and he's trying to fill out paperwork, and he can't do it without me. So, just sorry, one moment, please. Take a look at the other graph. It is a piecewise function, and you'll notice that as you move from one side to the other, there is a missing piece. There's a gap. That's called a break in the graph, which means there's going to be a break as we're moving from one side to the other. My God. Ladies listening to this, you will relate. I have had this conversation with my husband like 5 times already, and he's asking me the same question over and over again, and it's just making me laugh because we've talked about this. Okay, we're gonna do this again. Same deal. Domain first. Let's see. I got red, blue, and green. Let's get a different color. Let's get purple. Okay. So domain. Again, for domain, we start on the left-hand side of the graph. The leftmost thing on the graph is this. It's a closed point. Closed point is square brackets, and the x coordinate is -5. So we've got square bracket -5, comma. Now, this time, as I go from one side of the graph to the other, I'm kind of walking along and I climb up this hill, and then I get to here, and then, oh my gosh, all this stuff right here is missing. That's a big gap. That means that I can't get straight to this. I kind of have to jump over to get to it. If you have to jump and you don't just kind of fall and land, you got to like actually jump over a big giant gaping hole. There is a missing chunk in your graph. And that means you're going to have to close the interval here and restart it here. When you have a break in your graph, you're going to use a union to connect the two different pieces. So let's see, I go over to this point, that's an x coordinate of 1. Close point, so square bracket. Union to make the jump, that's the connection. Now, when I land over here, I'm on an open circle. That's called a hole in the graph. So we want to get real close to it, but not actually touch it. Use a round parenthesis to indicate that. And the x coordinate there is 2. So we're at 2, comma. And now we can kind of just walk straight down to the ending point, which is this guy. X coordinate here is 5. Close point, square bracket. So part of the graph goes from -5 to 1. Then we've got a broken part here, and then 2 to 5. And that's your x's. Now, erase all this stuff so we can talk about the y's. So y values go from low to high range. The lowest thing on the graph is this guy here. And now we want his y coordinate because we're talking about how low we go, -2. Close bracket, -2, comma. Now, as we make our way up the y's on this coordinate plane, we've got a y at -1 and at 0. There's some y's at 0 over here too, so we're good. There's y at 1. Here's a y at 1. Now, there's no y at 2 over here, but it doesn't matter because there's a y at 2 right here and a y at 3 right here. So as long as you have a y value on part of your graph, there's no break vertically. There was only a break horizontally. And this thing here is the highest point on the graph, y value +4. Solid point, square bracket. So if you have a broken graph, you kind of have to manipulate the way you're looking at it, depending on, excuse me, depending on kind of how you are, or which one you're trying to do. So some people like to turn the graph and always be going from left to right, even when you're looking at the range. That's fine. But I recommend just getting comfortable with going from left to right and then bottom to top. And we'll see some more stuff about range again later, or domain and range again later. But that was just kind of like a little intro to it. Now, given some functions. Sometimes we're going to be asked for domain and range of a function, and other times we're just going to be asked for the domain. If you are asked for both domain and range, I recommend drawing a picture of the graph instead of trying to guess and check. It's easier to do it when you're looking at a picture. Now, if you're just asked about the graph, about the domain, then there are some things that you can look for. There are 3 scenarios that we are going to have here. First scenario, rational equations. Second scenario, radical equations. Third scenario, everything else. So, if you have a rational, we got to be concerned about this stuff. In a rational equation, your denominator cannot be equal to 0. Rational equations are equations that have a variable in the denominator. And if you have a variable in the denominator, there is the possibility of ending up with something undefined. So what we do is find the value or values that make the 0 and remove them from the domain. These are called excluded values because they're taken out of the entire domain. Second scenario, radical equations, specifically square root equations. Even root indices can have a problem. So when you're dealing with even roots, you have the possibility of getting an imaginary. Because remember, when you try to take the even root of a negative, you get an imaginary number. And you can't have imaginary numbers in this situation where we're dealing with functions. So, in order to kind of eliminate that possibility, we force the radicand to be greater than or equal to 0. We make it be positive, and that becomes our domain. Third scenario, everything else. All other equations are going to have domain all real numbers. There is one exception to this that we are going to see, and I'm going to explain why it's an exception when we get there. But for the most part, everything else, negative infinity to infinity. And that's how you would write that in interval notation. So we're going to see these different scenarios, and then we're going to talk about finding domain and range, which again, I recommend doing a picture of a graph, whether you draw it by hand or use the graphing calculator or throw it into an online graphing thing, whatever you need to do to be able to look at it. But you can always graph and make a table and just kind of take a look at what you have. I always recommend looking at a picture when you can. If you take me for pre-calc, I draw pictures like everywhere because I like to look at stuff. So let's talk about just domain first, and then we'll get into domain and range. So we've got three scenarios here. Finding the domain. First scenario, f of x equals 1/5 x squared minus 5. Now, the question that I ask myself when I'm dealing with this is the function I'm looking at rational or radical? If the answer to either one of those questions is yes, then I have some stuff to do. If the answer to both of those questions is no, then I can stop because this falls into the other category, which means that the domain is all real numbers. This is a quadratic equation. It does not matter that it has a 1/5 at the front. 1/5 does not make it rational. It would have to have a variable in the denominator, which it doesn't. So you're in good shape. It's okay. And it's all real numbers. Second example is this guy right here. So again, I ask myself, is it rational or radical? This time the answer is yeah, this is rational. Rationals are one of the things that has a problem. So we have to do work here. The work for a rational is to find the excluded values. We talked about excluded values back when we solved rational equations. So this is not a new thing. This is like review. To find the excluded values, you take the denominator and set it equal to 0. This x squared minus 4x minus 5 equals 0 is a quadratic equation. And it is solvable using quadratic methods. So factoring, completing the square, quadratic formula, whichever one you prefer. I prefer factoring, and this is factoring. It factors into x minus 5, x plus 1. And then we set each one of these equal to 0, and I get two excluded values. X equals 5 and x equals negative 1. Now, we can't leave it like this. These are the excluded values. So we have to write this in interval notation. The interval notation for this, wow, there are people having way too much fun out there. The interval notation for this goes from negative infinity up to the first lowest excluded value, which is negative 1. Cut it off, union. Lower one to higher one, cut it off, union. Higher one to positive infinity. This weird little round parenthesis union thing means that we're getting really, really close to that value but not touching it and kind of scooting around it to the other side on the number line. Then we continue with our little walk, scoot around the next one, and keep going. These are the only two values that problem, so they're the only ones that have to be excluded from negative infinity to infinity. So there's your domain. Third scenario. Back to my question, is this rational or radical? The answer is yes. Radical. Square root. Square roots have a problem. So we're going to solve the problem by taking the radicand, that's the stuff under the radical, and forcing it to be greater than or equal to 0. That way, there's no way it can be negative. We're fixing it. We just have to solve this equation here, or inequality. So we subtract the 9 over. I get negative x greater than or equal to negative 9. And now we have to be careful here because we're dividing everything by negative 1. When I divide an inequality by a negative, the inequality symbol switches directions. Negative 9 divided by negative 1 is 9. So we've got x is less than or equal to 9. That means it starts on the left at negative infinity and makes its way up to positive 9. But 9 is the last place it can go, so we close it off. Now, this one is allowed to be a square bracket because of the inequality symbol, less than or equal to. So we're allowed to have this square. So there are your 3 scenarios. So you can see all 3 of them. In 4 and 5, we're talking about domain and range. So again, I prefer to look at it with a graph just to have a better idea of what the picture looks like. And that's going to help us determine what the domain and range are. Now, I have to pause here for just a second because I am like 9 months pregnant and have to run to the restroom. So I'm going to pause here and then pick up right here for the last little bit of this in a second video. So you'll have 2 links for this, but it will cover everything. So just kind of sit tight for a sec and I'll be right back.